Right now, 49 years after it left Cape Canaveral, a machine smaller than a compact car is moving through the dark at almost 38,000 miles an hour, carrying a golden record that no living hand will ever touch again. It has already outlived its creator's wildest promises. It has already seen worlds no human eye had witnessed before. But here's the question almost nobody is asking out loud. What happens after we go silent? Not what Voyager 1 has already seen, what it is going to see, or fail to see, across a timescale so vast that human civilization itself becomes a single flicker inside it. 1 trillion years is coming, and Voyager is already on its way there. Understand something first? Because this is where most explanations get it wrong from the very beginning. Voyager 1 is not simply flying through space, the way people imagine a rocket flying. It has no engine pushing it anymore. It has no more course corrections planned. What it has is momentum, borrowed from a gravitational slingshot around Jupiter and Saturn nearly half a century ago. And that momentum is now the only thing carrying it forward, forever, into a future that dwarfs every empire, every civilization, and every star we can currently see with the naked eye. Think about what that means. A machine built by engineers who are now retired or aging or already gone is going to keep moving long after every trace of the country that built it has turned to dust. According to NASA's own mission tracking, in just a few months from now, on November 18th, 2026, Voyager 1 will cross a threshold no human-made object has ever crossed before. It will become so distant that a radio signal traveling at the absolute speed limit of the universe will need a full 20s. Why 4 hours just to reach it? NASA now lists the exact moment as 2:16:07 a.m. Pacific time on that date. Read that again. Not 24 hours to send a message and get an answer. 24 hours one way. A whisper sent from a control room in California will spend an entire day crossing nothing but emptiness before it even reaches its target. And that is only the beginning of the story, because this milestone is not the finish line. It is barely the starting gun. Here's where it gets worse, and where most people misunderstand what's actually happening. Some assume this light day distance means a Voyager is LE, leaving the solar system, the way a plane leaves an airport. It already left the protective bubble of our sun's solar wind back in 2012, becoming the first human object to enter true interstellar space. But the sun's gravity does not stop at some clean, dramatic line. It reaches out for trillions of miles beyond that point, weakening, fading, but never fully letting go. A light day works out to roughly 25.9 billion kilometers, or about 16.1 billion miles. And that number, staggering as it sounds, is just a unit of measurement for a spacecraft that is going to keep moving for a length of time human minds were never built to comprehend. Now picture the control room itself, because this is where the human cost of distance becomes real. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, described what daily operations actually feel like at this range, and her words should unsettle you more than they comfort you. She explained that if she sends a command and says, "Good morning, Voyager 1," at 8 in the morning on a Monday, she will not hear Voyager 1's response until 8 in the morning on Wednesday. Not a delay of minutes, not a delay of hours. A round trip that eats an entire work week's worth of waiting for 2 sentences of conversation. Every single command now operates on a 48-hour cycle of silence before any acknowledgement comes back. This is not science fiction pacing. This is the literal, current, operational reality of talking to the most distant machine our species has ever built. But here is where the story shifts from distance to survival. And this is the part almost nobody outside the mission team fully grasps. Voyager 1 is not dying from age in the way a car dies from rust. It is dying from a very specific, very predictable countdown clock that has been ticking since the day it launched. Inside it sits a radioisotope thermoelectric generator, a device that converts the heat of decaying plutonium into electricity. That plutonium decays whether anyone wants it to or not, and there's no refueling station out there in the dark. Engineers say the spacecraft loses about 4 watts of power every single year, a number that sounds small until you understand what 4 watts actually costs a machine running on fumes. 4 watts a year does not sound dramatic until you watch what NASA has actually had to do about it. One by one, instruments that have operated almost continuously since the Carter administration are being switched off forever, not because they broke, but because keeping them alive would kill something more important. The cosmic ray subsystem was shut down to save power in February of 2025. Then, in a moment that mission engineers described with real weight in their voices, the low-energy charged particles experiment was powered down on April 17th, 2026, after functioning almost without interruption for nearly 49 years. This is not a settings adjustment. This is a slow, deliberate amputation of a living mission, instrument by instrument, to buy a few more years of a heartbeat. And this is where everything changes, because by April of 2026, the numbers had become almost impossible to ignore. NASA's own status table listed only 2 science instruments still functioning on Voyager 1, the magnetometer and the plasma wave subsystem. 2 instruments. Out of an original suite that once photographed the rings of Saturn and the volcanoes of Io, what most people are not seeing, what almost never makes it into a casual headline, is that engineers are not just watching this decline happen. They are actively fighting it, testing an experimental fix nicknamed the Big Bang, designed to reroute power in ways the spacecraft was never originally built to allow. The hope is that this upgrade could extend the aging probe's lifespan and, in theory, even allow some shutdown instruments to be switched back on. Notice the caution in how that plan is being handled, because it reveals just how fragile this entire operation really is. Engineers chose to test the Big Bang fix on Voyager 2 first, since it has slightly more spare power and sits closer to Earth, it making it the safer of the 2 spacecraft to risk. Only if those tests, scheduled through the spring of 2026, succeed, will the team attempt the same maneuver on Voyager 1, and even then no earlier than July. This is a team gambling with a 49-year-old machine that cannot be repaired, cannot be replaced, and cannot be reached by anything faster than light. One misstep, one command sent into that 24-hour void that behaves unpredictably, and decades of data collection could end in an instant, with no way to know why until it's already over. Here is the moment where the entire narrative pivots from present-day survival to something almost unbearably larger. Even in the best-case scenario, even if every experimental fix works exactly as hoped, mission scientists are honest about the ceiling on this story. Voyager 1's power will run out. Not might. Will. Most projections point to sometime in the early 2030s, a handful of years from now when the plutonium finally decays past the point of producing enough electricity to power even a single instrument, a single heater, a single transmitter. At that moment, the most important act of communication in human history simply stops, not with an explosion, not with a dramatic failure, with silence. And that silence is where most explanations end, because most people assume that once Voyager stops talking, the story is over. This is the single biggest misunderstanding about this mission, and it is exactly the misunderstanding this deep dive exists to correct. On Voyager, 1 going quiet does not mean Voyager 1 stops moving. The spacecraft will still be out there, blind, mute, powerless, but very much intact, still carrying the same momentum it picked up from Jupiter and Saturn decades earlier. It becomes, in that instant, something closer to a monument than a mission. A cold, dark, tumbling artifact carrying humanity's most ambitious message further into the void than any living person will ever witness. That message deserves its own moment, because it is easy to forget it is even there, bolted to the side of a machine most people only think about in terms of data and distance. The Golden Record, a gold-plated copper disc designed by a team led by Carl Sagan, carries greetings recorded in 55 languages, music drawn from across human cultures, scientific diagrams explaining who and what we are, and a map showing Earth's location relative to nearby pulsars. Think about what that actually means. Long after every government on Earth has changed, long after every language on that record has evolved beyond recognition or vanished entirely, that disc will still be out there, a time capsule addressed to no one in particular, and everyone who might ever find it. But here is the part that turns this from a sentimental detail into something almost eerie. That record, and the spacecraft carrying it, will continue traveling outward indefinitely, until some chance encounter with a star, a planet, or another civilization, potentially millions or even billions of years from now, not decades, not centuries, potentially billions of years. This is not a mission with an ending anymore. This is an object that has effectively become part of the galaxy's own permanent architecture, as real and as enduring, on cosmic timescales, as a comet or an asteroid, except this one carries a message deliberately written by a species that will not be alive to see it delivered. So, what does Voyager actually encounter out there, once it goes dark and the decades start turning into millennia? This is where the timeline stops feeling like engineering and starts feeling like prophecy. Somewhere between 20 and 30,000 years from now, long after every currently living human being and their grandchildren's grandchildren are gone, Voyager 1 will finally pass through the Oort cloud, the vast, distant shell of icy debris that marks the true gravitational edge of our solar system. For the first time since launch, the pull of other stars will begin to matter more to its path than the pull of our own sun. It will be, in the truest sense, leaving home. Then, in a moment, researchers can already calculate with startling precision. Something almost poetic happens. Gliese 445, a red dwarf star currently 17.5 light-years away, is actually moving toward our solar system, closing the distance Voyager will eventually need to travel. In roughly 40,000 years, Voyager 1 will make its closest approach to that star, passing within about 1.6 light-years of it. That is still an enormous gap by any human standard, but on a galactic scale, it is a near miss, a spacecraft launched by 20th century engineers brushing past an entirely different sun in the deep, deep future. And here's the detail almost no one talks about. It will happen in total silence, with no instruments left to record it, no camera left to photograph it, no way for anyone, anywhere, to know what happened except through math calculated centuries in advance. But here's where it gets worse, or perhaps more astonishing, depending on how you look at it. 40,000 years is nothing compared to what comes next. Researchers have calculated that Voyager 1 will encounter a main sequence star called TYC 3135521 in around 303,000 years, passing within roughly 0.965 light years of it. 300,000 years. To put that into perspective, that is longer than Homo sapiens has existed as a species on this planet. An object built by human hands will still be drifting, still intact, still carrying its golden message long after that encounter happens, with no one left who remembers why it was ever sent. And this is where everything changes again, because you might assume that eventually, given enough time, gravity simply pulls Voyager into a star and ends the story. It does not, at least not on any timescale that feels remotely human. The research team behind these calculations concluded that the actual timescale for a spacecraft like Voyager to collide with a star is on the order of 10 to the 20th power years, a number so large it stops meaning anything intuitive. Their own conclusion was almost understated. The spacecraft, in their words, have a long future ahead of them. That single sentence, buried in a scientific paper, might be one of the most quietly staggering statements ever written about a human-made object. Now stretch your imagination forward from those hundreds of thousands of years into the territory this story actually promised you, 1 trillion years. What does the universe even look like by then? And would Voyager, if it somehow still had working eyes, recognize any of it? The first thing worth understanding is that the galaxy Voyager is drifting through will not stay the same shape it is in today. For decades, scientists treated a collision between the Milky Way and the Andromeda Galaxy as an almost certain event, a slow-motion cosmic collision predicted to arrive in roughly 4.5 billion years. That was the story told in documentaries, textbooks, and planetarium shows for a generation. Except that story just changed, and this is exactly the kind of update that separates a lazy explanation from one built on current evidence. A 2025 study using updated Hubble and Gaia telescope data found only a 2% probability that the Milky Way and Andromeda will collide within the next 5 billion years, directly contradicting the long-held assumption that the collision was essentially guaranteed. Lead researcher Til Sawala and his team combined the motions of the 4 largest galaxies in our local group, along with updated mass estimates to reach this conclusion. What most people still believe about our galaxy's fate is, according to the newest data available, no longer considered reliable. Sawala's own reaction to his team's findings tells you everything about how seismic this shift really is. He admitted that he was prepared to find something different, and that discovering only roughly a 50-50 chance of a merger was genuinely surprising to him. Not a minor revision, a complete collapse of certainty replaced by a coin flip. The study's own language, published in Nature Astronomy, stated plainly that proclamations of the impending demise of our galaxy seem greatly exaggerated. Somewhere out there, Voyager 1 may drift through a Milky Way that never collides with Andromeda at all, cutting quietly through open space in a galaxy that stayed exactly where it was, defying what an entire generation of scientists once treated as inevitable. But even if that merger never happens to our galaxy directly, something else almost certainly will, and it happens on a timeline far closer to us. Researchers concluded that a merger between the Milky Way and the Large Magellanic Cloud, our galaxy's largest satellite, is nearly certain within roughly 2 billion years. Sawala described this coming event vividly, explaining that such a merger would likely involve a massive burst of new star formation, followed by intense radiation from exploding young stars and a newly reactivated supermassive black hole at our galaxy's core, eventually shutting down star formation entirely. Voyager will not witness this either, not with instruments, not with eyes, but it will be there, tumbling through whatever transformed galaxy results from it, an artifact from before the rearrangement, older than the new shape of its own home. This is not chaos. This is strategy written by physics itself, unfolding across a scale that makes human history look like a rounding error. And once you accept that framework, the deeper future starts to come into focus, layer by layer, each one stranger than the last. Star formation itself, the very process that built every sun Voyager might ever pass, does not continue forever. The raw material for building new stars, the vast clouds of hydrogen scattered across galaxies, is finite, and it is being consumed faster than it is replenished. Scientists refer to the current period of cosmic history as the stelliferous era, the age of stars, and every projection agrees it has an expiration date. Think about what that actually means for a spacecraft with no endpoint of its own. Somewhere in the range of 1 trillion to 100 trillion years from now, astrophysicists expect the last new stars to form, ever. Not the last stars to exist, but the last stars to be born. After that threshold, the galaxies Voyager drifts through will contain only the stars already made, slowly burning down like candles nobody is replacing. The brightest, most massive stars will have died in supernovae long before this point. What remains will be dominated by the dimmest, most miserly stars in the universe, the red dwarfs, sipping their fuel so slowly that some of them are expected to burn for tens of trillions of years before finally fading. And here's the detail that should genuinely unsettle you, because it directly ties back to the very star Voyager is already aimed toward on its slow journey outward. Gliese 445, the red dwarf it will pass in 40,000 years, belongs to exactly this category of star, the kind built to outlast almost everything else in the cosmos. Read that again. The star. Voyager brushes past in a time frame that already sounds impossibly distant to us, is itself one of the very stars expected to still be burning, faint and patient, when the stelliferous era finally winds down over 1 trillion years from now. Voyager's first close encounter and the deep future of star formation are connected by the same stubborn, slow-burning class of star. Once the stelliferous era ends, the universe does not simply stop. It transforms into something almost unrecognizable, a period scientists sometimes call the degenerate era. Stars stop forming. The ones that remain slowly cool and darken, collapsing eventually into white dwarfs, neutron stars, or black holes, the dead husks of everything that once shone. White dwarfs themselves, over spans of time that make even Voyager's 300,000 years star encounter look instantaneous, are expected to cool into what astronomers call black dwarfs. Cold, dark, crystallized remnants that no longer emit meaningful light at all. If Voyager somehow still had functioning cameras 1 trillion years from now, and it will not, but if it did, it would be staring into a sky growing darker with every passing epoch. Galaxies filled not with brilliant points of light, but with slowly extinguishing embers. But here's where it gets worse still. Because light is not the only thing fading. The universe itself is expanding, and current evidence suggests that expansion is accelerating, driven by whatever mysterious force scientists label dark energy. Over trillions of years, that expansion pushes distant galaxies away from each other faster than light itself can bridge the growing gap between them. This means that whatever galaxy cluster Voyager eventually finds itself embedded in, all the other galaxies beyond it will slowly vanish from any theoretical vantage point, not because they stopped existing, but because the space between everything is stretching too fast for their light to ever arrive. 1 trillion years from now, an observer sitting where Voyager drifts would see a night sky that is almost entirely eerily empty, populated only by the fading, merged remnant of its own local galactic neighborhood. This is the real answer to the question buried inside this story's own title, and it is far stranger than most people expect. What Voyager 1 will see in 1 trillion years is not a spectacular alien vista or a dazzling new star system. It is closer to nothing at all. A cold, dark, silent void populated by dying embers of stars long past their prime, drifting through a Milky Way that may or may not have merged with its neighbors, carrying a golden record whose 55 languages will have long since been forgotten by whatever, if anything, remains of the species that recorded them. The most extraordinary part of this story is not what Voyager encounters. It is that it keeps going regardless, indifferent, unaging in any way that matters, an object that outlasts stars. And that is precisely why this mission matters more than almost anything else humanity has ever built. Every rocket, every monument, every written language we've ever produced is tied to Earth, vulnerable to Earth's fate, bound by Earth's timeline. Voyager 1 is enoistet, ought. The moment its power finally runs out, sometime in the coming years, it does not die in any meaningful sense. It graduates into something closer to a fossil in motion, a piece of 20th century human ambition, set loose into a universe that will still be unfolding long after the sun that gave it its escape. Velocity has swollen, died, and cooled into darkness itself. So here is where this story has to leave you, because the truth is nobody, not the engineers at JPL, not the astrophysicists modeling galaxy mergers, not anyone alive today, can tell you with certainty what waits for Voyager 1 in the deep, deep future. Will some future intelligence, human or otherwise, ever intercept that golden record and understand the greetings recorded on it? Will the star systems it passes contain anything, or anyone, capable of noticing? Will the very physics governing dark energy and cosmic expansion hold steady across trillions of years? Or does something even stranger wait in the mathematics we haven't discovered yet? Voyager 1 is still out there right now, this week, drifting toward that first light day milestone. carrying a message none of us will live to see delivered into a future that has already been calculated in fragments but never fully understood. And somewhere between now and 1 trillion years from now, in the cold and the dark and the silence, it just keeps moving.